All right, picking up where we left off. If you notice, this has no minimum or maximum. Okay, it keeps going forever and ever. Okay, so that means it does not have a lowest or highest point. However, if I restrict the domain, in other words, I tell you that x cannot be anything less than 1, then that means that at 1 in this particular function, you have a minimum. You have a minimum at 1/6 or 1-6. Sorry, at y equals -6. So your minimum is your lowest y value. Your maximum would be your highest y value. This would not have a maximum. It keeps going forever and ever in that direction. Okay. All right. Functions that represent real-world scenarios often include domain restrictions. That's what we were just talking about. Okay. For example, if we were to calculate the cost to download a number of ebooks, we would not expect to see negative or fractional downloads as values for x. There are several ways to classify numbers. The following slide list, make sure you know these guys. Most of these you should know, but some of you won't. Don't worry about the notation. I know it looks a bit weird or whatever. Natural numbers, 1, 2, 3, 4, right? That's your basic counting numbers. When you talk about whole numbers, you include 0, okay? Integers, you include positive and negative whole numbers. Rational numbers are numbers that can be written as a over b. B cannot be 0. So basically, you can write, that includes fractions and decimals, okay? So rational numbers, fractions, and decimals, all right? So that end or repeat, so be careful there. So irrational numbers are decimals that don't end and are not repeating. So things like pi, 3.14, blah, 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 right? There are plenty of other examples of that, but decimals that don't end, basically, is what you're talking about when you talk about irrational numbers. We're going to be focusing mainly right now on everything but the irrationals. Okay, when we talk about graphing and domain and range, that kind of stuff. All right, so an exponential function in the form f of x equals a to the x power, where a is greater than 0 and a is not 1. Okay, if that's the case, it has an asymptote. Okay, or a line that the graph gets closer but never crosses. Basically, we talked about how those curves flatten out, but they never reach a specific number. In all of the examples we've done so far, it's been 0. Okay, that's called an asymptote. Okay, specifically for exponentials, it's a horizontal asymptote. You'll get later on where you'll learn about things called vertical asymptotes. But for what we're doing right now, everything's going to be horizontal. Okay. The function in the following graph has a horizontal asymptote at y equals -4. Basically, that means it approaches -4 but never gets there. It may appear as though the graph line touches it, but it never really does. So, taking a look at it, this is what we're talking about. This line right here, okay, that y equals -4 line is the horizontal asymptote for this function. Okay? All right. Example 1. A taxi company in Atlanta charges $2.75 per ride plus $1.50 for every mile driven. Determine the key features of this function. I'm going to go through them very quickly, but you're going to need to keep this graph in mind. Okay? So, some key points here is it starts at 0. The cost will be $2.75. Okay? And I've seen a lot of you do this. Just because it says per, a lot of you have been taught this, and it's kind of a bad thinking process. Per something does not necessarily mean that that's going to have a variable attached to it, right? In this example, we're talking about a single person going on a ride in a taxi, right? That's one ride, which means that the 2.75 is a constant, right? It does not have a variable attached to it. Okay, our equation for this would be the total cost of your trip is 50 cents or $1.50 per mile plus your ride fee, which is $2.75. Okay, you're not taking multiple rides in the cab. You're only taking the one ride, which means this per ride part is really just filler, right? It's a fee to ride, one-time fee. Okay, that's important. Some of y'all see that word per and you think, oh, I better attach a variable to it, and that's a hint. That's not a guarantee. Okay, a lot of times it says per, that does mean that it needs a variable, That is not always the case, right? Technically, right here, they could have said per mile, right? It's $1.50 per mile. Up here, it was per ride. That doesn't mean they both need a variable because you're only taking the one ride, okay? All right, so let's talk about the key features. We can see by the graph the function is increasing, right? As I went from left to right, it was going uphill. And we see that it's linear, it's a straight line, right? The next thing we can identify are the intercepts. The graph function crossed the y-axis at 0 to 2.75. It does not cross the x-axis, so there's no x-intercept. Okay? Determine whether the graph function is increasing or decreasing. Again, we already said that. From left to right, it was increasing. The y values are going uphill. Determine whether the function is positive or negative. Well, if it never crosses the x-axis and it was always above the x-axis, that means it was always positive. But our x has started at 0, so when x is greater than 0, it's positive. And there's never negative, so it's not ever negative. Determine the relative maximum min. So it started, it had a lowest point, but then it's going to keep increasing based on the number of miles you go. So if you don't go anywhere, you just get in the cab and then get right back out, which is kind of silly. But if you did, you'd have to pay them $2.75. Okay? There is no relative max, but there is a relative min. Identify the domain. Well, domain is the x values. Can't travel for negative miles, so it's got to be greater than or equal to 0. Technically, you could get in and then get right back out, although, again, that would be kind of silly. The graph is linear, not exponential. We know that because it's going uphill, right, in a straight line. It's not a curve. And since there's no curve, that means that it does not have an asymptote. All right, let's take a look at example 2. Guided practice. The pendulum swings at 90% of its height on each swing and starts at a height of 80 centimeters. The height of the pendulum in centimeters is recorded after X number of swings. Determine the key features. So again, we're just going to go through some of them. But what I want to point out first is, I'm going to go ahead and say it now even though it's going to happen again, or I'm going to mention it again. This is exponential. Anytime you're doing 90% of something or a percentage of something, right, that means it's going to be multiplied by that percentage each time. Okay, you would do 80 times 90%, which is 72. Then times 90% again, which is 64.8. So I know for a fact that this is already exponential. Okay, that's just from me doing it in practice, but I'm just telling y'all that for the sake of the example. You can do this in your calculator to kind of figure out what it would be. All right, so here we go. The scenario described is exponential that I talked about. You can also see from the table of values that it's not decreasing at a constant rate. Okay, you're not repeatedly adding or subtracting. So 2, identify the intercepts. Okay, well, back in that table we had 0, 80, right? Which meant that's your y-intercept. Okay, as your x is increased, the value gets closer and closer to 0, but does not seem to reach 0. Therefore, there is not an x-intercept. Okay, that never crosses. It gets close to it, but never does. Since the values in the y are getting smaller, we know that this is decreasing. Determine where it's positive and negative. Well, got to be when x is greater than 0 because we don't have any negative domain values for this one. The y values seem to always be positive. The highest one was 80, and then it increasingly got closer and closer to 0, but it never gets to 0. Okay, so it never is negative. So it's positive for all values where x is greater than 0. It's never negative. Relative min and max. The data in the table do not change at a constant rate, therefore the function is not linear. Based on this information, we know this is exponential. Exponential functions do not have a relative minimum because the graph continues to become infinitely smaller. Even though it's closing in on 0, it can always get closer and closer to 0. Right? It can always get closer and closer to 1 over some gigantic number. So we have an infinite, it goes out to infinity in that direction, so it gets infinitely closer to 0. Now, on the other side of things, we did have a highest point, which was 0, 80. Right? So we have a relative max for this one. Domain, again, the lowest x value increases infinitely. X can be any real number greater than or equal to 0, but it cannot be a partial swing. So that's why this is important. So the domain here is all whole numbers. Okay, any number greater than or equal to 0. Okay. All right. The asymptote is what it's approaching. Again,